Hey, this is Horner. We're going to look at the problems we were not able to get to in class. So you and the moon, you're on the moon, and you'd like to send a probe into space so it does not fall back to the surface of the moon. So what is the launch speed that we need for this? If you look at example 6.8 in your book, they will go through the derivation of an equation. So they'll go through and show you how they got this equation. The escape speed from any massive object is equal to 2 times the universal gravitational constant times the mass of that object divided by the radius of that object. And because we're dealing with the moon, we can just plug everything in here for the moon. Notice that you don't have to worry about the space probe's actual mass. If it's small enough compared to the mass of the moon, then relatively speaking, it could be almost any mass, just as long as we don't get really too close to the mass of the object we're trying to launch off of. So this is 2 times 6.67 times 10 to the negative 11th. Then we multiply that times the mass of the moon, which is 7.35 times 10 to the 22nd. All of these numbers will come off of either an equation sheet or some data that I would have to give you. And then the radius of the moon is 1.74 times 10 to the 6th. So if you do that, you're going to find out that you get about 2,370 meters per second, or 2.37 kilometers per second. For the next question, this one takes a little bit of math to do, a little different math understanding. Same type of question, they give us a radius, but they also give us a gravitational field, which means they just want to tell you that gravity on this planet is 30 meters per second square. So that's 3 times as much as what you experience on Earth. We're going to use the same equation again. The escape speed is equal to the square root of 2 times g times m all over r. And we know that g, the equation for gravity, is equal to big G times big M all over r squared. So what we want to do is we want to turn this thing into gm over r squared. So, or we want to take this and reduce it down to this. Either way you look at it, to do that, what you can do is you'll say 2 times, and then we're going to put in our equation for g, which is big G, big M all over r squared. Oops, all over r squared. And then we've got to multiply it by something so that we're left with this when we do all of our math. So if you multiply this just by r, that r and that squared will go away and you're equal to our original speed equation. So we're going to just manipulate, we've manipulated the equation a little bit. Since we have this number and we don't have the mass and the radius, to go through and just do it this way. All right, so here's what we're going to do. We know this is equal to the square root of 2 times, now we said big G, big M all over r squared is equal to 30. So that's 30. And then they did luckily give us the radius, and it is 6 times 10 to the 7th. So we had to do this one this way because we never had the mass. We never had the mass. One thing that we could have done was we could have also plugged 30 in here, plugged in 6.67 times 10 negative 11th, put m on the outside, and then taken our radius, which is 6 times 10 to the 7th, and then squared it. We could have found the mass that way and then just plugged it into the original equation. So either way you go, you would be fine. When you're done, you're going to end up with about 60,000 meters per second, or 60 kilometers per second. So that's number 43. Number 44 is number 53 is a lot simpler. We have an ideal spring, and that ideal spring has a spring constant of 20 newtons per meter. What is the amount of work that must be done to stretch the spring 0.4 meters from its relaxed length? To do this, we're just going to use our equation for the work done by a spring, which is also equal to the potential energy of a spring, which is equal to 1/2 kx squared. This would be 0.5 times our 20 Newton meters, and then we need to multiply that times 0.4 meters squared. So that would be equal to 1.6 joules. And that is all that you need to do for number 53. Next question is number 56. This one is a little different. This one's nice because it's got a kind of a physical therapy biology stint to it here. It says that if the length of the Achilles tendon increases 0.5 centimeters when the force exerted on it by the muscle increases from 3,200 to 4,800 newtons, what is the spring constant? So here we are looking for the spring constant, which is K. We're going to say that K is equal to F over X, and that comes from our equation for a spring. Force of a spring is equal to the spring constant times the stretch. Our force here is 4,800 newtons minus 3,200 newtons. So we're trying to find out what is the force, the overall force, when it has the increase in tension on that muscle of 3,200 to 4,800. So we need to find the difference between the two. So we find out what the actual force is stretching that Achilles tendon, and then we need to divide it by our stretch length here. So we know that 0.5 centimeters should be equal to 0.005 meters. So when we do this, we're just going to say this is divided by 0.005. And so you're going to end up, so that should give you about 320,000 newtons per meter. So pretty big spring constant. Let's go ahead and take a look at letter B. For letter B, it says how much work is done by the muscle in stretching the tendon 0.5 centimeters as that force increases from 3,200 newtons to 4,800 newtons. So the first thing we need to do is let's just figure out how much that tendon is already stretched with our original force of 3,200 newtons. So that's the first thing we're going to do. Let's go ahead and put in the original stretch should be equal to the force over the constant. The original force is 3,200, and our constant here is 320,000. So our original stretch was 1 centimeter, which is 0.01 meters. Our final stretch here, then, since we went up by 0.5 centimeters, is going to be 0.015. Now we know that the work done by a spring is really just the change in the potential energy of a spring, and the potential energy in the spring here is equal to our final, so that would be 1/2 kx squared, and that's final, minus our original, so 1/2 kx original squared. Notice we can factor out the 1/2 k, and then we can just do x squared final minus x original squared. So this will be 0.5 times 320,000. Then we have our final, which is 0.015, and we have our original, so that's squared, minus our original, which is 0.01 squared. And so if you do your math, you'll end up with 20 joules. Let's go ahead and take a look at the next one. So that was number 56, A and B. This is number 60. It says a spring fixed at one end is compressed from its relaxed position by a distance of 0.2 meters. So there's our 0.2 meters. They want us to see the graph of the applied external force, Fx, versus the position x of the spring. Find the work done by the external force in compressing the spring 0.2 meters from its original position. So for letter A, this one we just know work is equal to the area, so that'd be 1/2. So we're just looking for the area of the triangle. 1/2 of, that doesn't really look a half. There we go. 1/2. Be easier just to erase it. So W is equal to 1/2 of the base, which is 0.2, times our height, which is 15. And so here you end up with about 1.5 joules. For the next one, for letter B, they want us to find the work done by the external force when it goes from 0.1 to that 0.2. And so we'll just take our whole area here, and then we'll just subtract off this little tiny triangle. So to do that in a couple steps here, W is equal to, we're going to do 1/2 of 0.2 times 15. That's what we did above. And now we're going to subtract off this little triangle here. So we could either find the area of this figure, or since we already have this, it's going to be easier just to get rid of that little guy right there. So this is 1/2 of 0.1 times 7.5 newtons. That 7.5 is approximately this point right here, which is halfway between the 5 and the 10. So when you're done, you're going to end up with 1.1 joules. Let's go ahead and take a look at the next one, which is the last one. This is number 63. It says the tension in a ligament in the human knee is approximately proportional to the extension of the ligament. If the extension is not too large, if a particular ligament has an effective spring constant of 150 newtons per millimeter. Notice this is in millimeters. They first want us to find out what is the tension in this ligament when it's stretched by 0.75 centimeters. So to find the tension in the ligament, tension is a force, so we're going to just say the absolute value of the force, and that's equal to the absolute value of K times X. That way we're not dealing with negatives here. Our K value they gave us was 150 newtons for every millimeter of stretch, since we're dealing with the knee and there's not a big extension here. We need to convert the 0.75 centimeters to millimeters. We just move the decimal place over 1, and so that's 7.5 millimeters. And now our millimeters cross off and we're left with 1,100 newtons. So that's pretty big tension. They want us next on this one for letter B for us to find out what is the elastic energy. So we want to know what is the potential energy due to the spring when it's stretched that much. So this would just be 1/2 K X squared. So that's 1/2 of 150,000 newtons per meter. So I had to convert this from newtons per millimeter, just multiplied by 1,000 and got 150,000 newtons per meter. And then we're going to multiply times the stretch, which is going to be 0.0075 centimeters, meters. So we went from centimeters to meters, and that is squared. So this is equal to 4.2 joules. And that is the end of the problems.